my intent with this session is to basically build this schematic. I want to show you how to use the breadboard, talk a little bit about the breadboard, and answer any questions that you might have. So, what I'd like to start out with is just showing you how I would build this circuit on the breadboard. And if you have any questions, just go ahead and unmute and ask them. There are only a few of us here on this session, so we can divert as needed. So to start out with, what I wanted to do is talk about kind of the basics, right? So when you have a couple resistors, I wanted to start out at this point because there's a video out there, but I didn't explain actually everything about making connections between components, and I wanted to start out here. So let's suppose you have two resistors and you wanted to connect these together. So you could actually lay these out on paper or twist the leads together and make connections. So those resistors right now with those two leads touching would be connected. That would be fine. It wouldn't be very rugged, wouldn't be very durable, but that would be a fine implementation of this circuit. It would work until, well, you shake the paper or sneeze. So, what you can do is you could also use wires, and again, you could lay one on top of another and one conductor on top of another, and as long as they're touching, that would also make a connection between these two resistors, right? So you'd formed a node with a wire. You could solder those together. You could twist those together. An easier way is to use a breadboard. So let me bring the breadboard in now. In fact, I'll zoom way in on this breadboard. So the way this breadboard works is there are certain holes that are connected. Holes are connected like this diagram. So this diagram is on the video that I posted. I think it was for lab 2. And so this diagram is oriented the same way as this breadboard. It's almost the same. It's not exactly the same as breadboard, but if you look at the holes are organized around kind of this valley here. If you look on either side of that valley, you have the way this breadboard is oriented, rows of holes. So the hole where my pencil is connected to electrically connected to the hole right next to it to the right, and the one to the right. So all of those 5 holes are all electrically connected. That row is isolated electrically. It's not connected to the other rows. So the row right below it is not connected right to the row above it. So if I wanted to take those same 2 resistors, if I can find my resistors, and I wanted to connect them together, I could do this. I could put a resistor in that hole, and then I could put a resistor in that hole. And so I have this, right? So I have those 2 resistors connected together on one side of each resistor. And again, stop me if you have any questions about this, but I could take this resistor, I can move it here. Those 2 resistors are still connected. I can move that resistor here. Those 2 resistors are still connected, okay? If I do this, those 2 resistors are not connected, because if you look at the number here, row 10 is isolated from row 9. So those resistors are not connected. They're connected to 2 different nodes, completely different nodes. So there could not be any current flowing through one resistor through the other, okay? But any one of these holes, right, to the right, they would be connected together. Okay, any questions on that? Okay, so there are other holes on this breadboard, and you can see actually physically on your breadboard, they're separate plastic pieces with metal underneath. But if you look at from where my pencil is now, let me slide that down a bit, where my pencil is, over to the other seam over here, that's really one breadboard component. The valley separates the rows electrically. In other words, these two resistors right now, those leads are not connected, okay, because this valley isolates the two sides of this section of the breadboard. Okay, so those are not connected. So these, if I put those resistors there, those are not connected. If I move the resistors over here to that side, so now those resistors are connected together. One lead of one resistor connects to one lead of the other resistor. You'll see that there are these columns that are different. It looks like a different, you can see a seam here. It's a different portion, a different piece of the breadboard. The conductors along this side, along the red stripe and along the blue stripe, actually connect vertically. Okay, so if I want to connect two leads together, I could do this. So those two resistors are connected together. I could do this. Those two resistors are connected together, okay? If I move this top resistor to the blue column, now those resistors are isolated, they're not connected together, okay? This breadboard in particular, if I zoom out a bit, has columns, right? Those columns there that extend from the very top of the breadboard down to the bottom. So that whole column is connected. You'll see some breadboards. Let me put this picture up of another breadboard. I drew these blue boxes here, but this breadboard in the columns actually has a separation here. And you have to check that with an ohmmeter or a voltmeter to make sure you know what your breadboard's doing. But there's a separation here. So you have actually 4 columns that are separate on the right to connect things to. Okay. All right, let's see what else about this breadboard. These terminals are not connected to anything. You can choose to connect those terminals. For example, you could take, they're screw terminals, so you could screw a wire into that terminal and then plug it into a node, right? Plug it into one of these. So now this top row is connected to this terminal up here. You could use a banana jack. We don't have those in our kit, but you could use a banana plug to plug into that banana jack and connect a wire from, let's say, a power supply down to that row. Okay. But I haven't been using those so far in this lab, so just wanted to point that out. Okay. So that's about it. All the rows of the groups of 5 are all connected together. They form a node, and they're all separate from the other rows when you cross valleys or cross over this center column of conductors here. Okay. Any questions on that? Those are kind of the basic connections between the holes on a breadboard. Okay. All right, so let's do this. Let me zoom in and I'll start building this lab. I'm going to bring my schematic. So schematic is really important. If I'm helping you troubleshoot a circuit, I will usually ask for a schematic because I want to make sure that the schematic is right and be able to match the schematic to what you've built in order to help troubleshoot. Okay, so we have, let me get it over a little bit more. Okay, so here's the circuit I'm building, and I want to build that on this breadboard. So what I like to do is start at one node. So what I'm going to do is I'm going to start at node A up here. And I do this. I highlight my schematic as I'm building it. I've been doing this for 25 years, and I still make mistakes if I don't highlight. So I've learned to highlight the nodes that I've connected, the components that I've connected. I'll show you how I do that as I build a circuit. Okay, so let's do this. I'm going to pick, let's say up here, that part of the breadboard, that horizontal row, that node, and that's going to be node A, right? So I've just made this connection right here to a wire. And so what I can do is I can start inserting resistors. So let's do that. Let me put this 2.2K resistor between node A and node D. Okay, so if I take this resistor and plug it in right there. So what I've done is I've connected this input road. I'm going to use that red wire as the input to the 5-volt power supply. I've connected that node to resistor R2. Okay, and so whenever I connect two components together, I am going to highlight that node. Okay, so let's now work on resistor R3, that 1.5K ohm resistor. So if you don't have one of these, go off the web and print out a cheat sheet for resistor color codes. It's really helpful. Instead of counting it out all the time, you can print out a color code cheat sheet if it's not already with your resistor packet. Some resistor packets contain that. So now I'm going to connect this 1.5K ohm resistor, right, like that. Okay, so let me bend that over a bit. So the top of that 1.5K ohm resistor connects to the left side of the 2.2K ohm resistor. Okay, because I've put those leads into the same row. So I'm going to go highlight that. So I'm going to highlight that connection right there. I've just created that connection between R2 and R3. Okay. Okay, so let's do, let's say R5, 1.8K ohms. Right. And there's no one way to do this, lots of ways to do this. Just I'm making this up as I go along. Okay, so now the right side of R5 connects to the bottom side of R3, at the bottom lead. So I've made this connection here. Okay, let's do R1. Let's connect R1 between node A and node C. So that's a 1K ohm resistor. And make sure the leads are all the way into that hole. If you just only insert that lead just a little bit, you might not make electrical contact. Okay, so I have connected node A to resistor R1, right? And I've connected resistor R1 to node C, and node C is also connected to the resistor R5. So I've just done this. Okay, makes sense so far? Stop me if you have any questions here. So I've been showing that putting this together by just using resistors, no wires. I can use some wires here though. Let's suppose I want to extend this node E down a little bit to give me some room. Maybe I'm getting tight on my circuit. So I've just extended node E, right? That node right there, down to this row, looks like 19. Okay. So let me insert a 1.5 k ohm resistor R6. Just do this. Okay, so now I have R6 in there. So I have connected the top of R6 to node E. And what I'd like to do is, well, let's just keep going here. Let's insert this R4 resistor 1.2K. This will finish off the resistors. So I'm going to extend this node down also. Extend node C down just for fun. And let's put, it doesn't matter, let's put that resistor right in there. So that's the 2.2 k ohm resistor, or no, that's the 1.2 k ohm resistor. So I've made this connection. R4 is now connected to node C. Okay, I'd like to connect a ground, right? Here's the ground. That ground is connected to the ground of the power supply. That'll be the black wire of the AD2. Okay, so I'm going to connect, let's see, I'll put just a brown wire there. That reminds me I'm going to connect a power supply there. Okay, so now I've connected, we're going to call that brown wire, this terminal B here. And I've connected the 1.2 k ohm resistor to that ground node of the power supply. Okay, so what I haven't done, I haven't connected the bottom of R6. R6, it's in the same row as the bottom connection of R4, but remember there's a gap here across the valley. There's an isolation there. So what I have to do is I have to connect the left row, looks like row 24 if you're counting numbers there, to the right side. So I have to do this. So just put a wire in there. So now I've connected the left and the right side of row 24. So now I just made the connection from the bottom of the 1.5 k ohm resistor over that way. Okay. And you have this ground symbol here. If in this case, for this schematic, this ground symbol just indicates a reference for the node voltages. So it really doesn't do anything other than point out that bottom node is the reference node for the node voltages. We'll get to this later, but sometimes you see a ground node and you also see a node voltage just written in, maybe just 5 volts next to this node up here. In that case, you'd have to connect the power supply explicitly to the ground node, and I'd probably highlight that ground node. But since we have the power supply drawn as a source with 2 terminals, this is good enough for now. We're just going to connect the power supply here. Okay, so there's that is the whole circuit without the power supply for lab 3. Anybody have any questions on that?
How do you know like where to ground it if the diagram doesn't explicitly say? Does that question make sense?
Let me see if I understand. Do you mean where do I connect the negative of the power supply? Is that what you're asking?
Oh, I guess so. Okay, actually that makes sense. I guess I was the negative of the power supply and the ground symbol were messing me up, but I understand now. Sorry.
Okay.
Thanks.
No, that's good question. So let me show you this. Let me block off this power supply. What you're going to see in the future is this. You're going to see no source explicitly drawn on some schematics, and up next to this terminal up here, it'll just say maybe plus 5 volts. Okay. And in that case, you would connect the power supply, the positive side of the 5-volt power supply, to this terminal, and you would connect the negative side of the power supply down to the ground node. So if no power supply is shown, but it's implicit, in other words, there's a node voltage with the voltage shown there, you would connect the power supply between 5 volts positive and the negative would go to ground. In this case, the power supply is actually shown as a voltage source, so you can just connect it like it's shown.
Okay, gotcha. Thank you.
Good. Okay, so other questions about the circuit. There's the whole circuit again. I'll connect the power supply up in a second, but that's the circuit.
So for the labs, I've been using the positive connection of the power supply and just the ground. Do I have to use the negative side of the power supply?
The ground is the negative side of the
Oh,
power
okay.
supply. Yeah.
All right.
Yeah, if you look at, let me bring the AD2 up here, see if I can get this up here. So where it says V plus and V, let's see, where it says V plus, that's the positive power supply's output terminal. The down arrow there is a ground symbol. So that's really the negative side of the power supply.
Oh, okay.
Okay, and the V minus is actually the negative power supply terminal, and its ground is also the down arrow.
Okay, so they're two
Yeah.
separate things.
Right. So what this is, in fact, let me show you that now. I'll draw something really quick here. Okay, so this is what those power supplies actually do. There are two power supplies with outputs V plus and V minus, right? So those are shown in the silk screen on this on the plastic here. So if I had the power supply set up, let's say for plus 5 volts for power supply 1, the positive supply, and if I had negative 3 volts set into the negative supply, I would measure plus 5 volts node voltage at the V plus terminal with respect to ground, and I'd measure minus 3 volts at the V minus terminal, right? The V minus terminal with respect to ground. And so it's like doing this. It's like taking a voltmeter, right? It's like taking a voltmeter. I'll just write VM here, connecting the positive side here, the negative side here, right? And then you'd be measuring V minus with that power supply. If I wanted to measure the positive power supply, put a voltmeter here, VM, put its plus terminal at the node where I want to measure the voltage, its minus terminal at the ground, and I would see plus 5 volts here. So this voltmeter, the green voltmeter, would read with this polarity minus 3 volts, and the top voltmeter would read plus 5 volts. Okay. And in your next lab, in your Thevenin lab, you're going to use both power supplies, so you'll see that there. Okay. All right. Well, let's fire this thing up. See if it works. See if I smoke anything here. So what I'm going to do is, so the power supply output terminal for the positive supply is that V plus, which is, let's see, the red wire, and the minus of the ground of the power supply, right, is the black wire right there. And there's a black wire there. You have a lot of black wires on this. And to measure voltages, for the voltmeter, the orange is the positive side of the voltmeter. That's that 1 plus. So voltmeter 1 plus is the orange. The orange wire with the white stripe is the negative side of the voltmeter. Okay. So you don't want to use ground for the negative side of the voltmeter because you don't necessarily want to ground a terminal when you touch the voltmeter to it. So the voltmeter measures the difference in voltage between the orange wire and the orange with the white stripe. Okay, so let's power this thing up. So what I'll do, so I'm going to take the V plus wire and connect it here. Let's see if I can get that in the shot.
Question, Professor.
Yeah.
Can you show us how to use the BNC cables? They're just really nice to hold, and I find that using the +1 and -1 connected to just leads or whatever is a bit it's annoying, I would say.
Oh, it's annoying. But why? Because they pull out.
Not necessarily. Just putting them in pins and checking quickly compared to the nice cables that we have, you know.
So I'm going to introduce that later. And the reason I'm going to introduce that later is because I don't want to add a potential source of error there. The potential source of error is the oscilloscope probe setting, the 1x versus 10x impedance setting. And so there's actually a 10 times voltage attenuator in that probe. And you have to make sure that you have a setting set a certain way in the AD2 software, in the waveform software, in order to not get a 10 times wrong reading. So I'll introduce that later. But for now, I want to stick to these. So you're welcome to use it. If it works for you, great. Go ahead and use it. But I'm going to stick to using the wires for now.
Sounds good.
Okay, so I've connected, remember I defined this red wire as the positive side of the 5-volt supply, right? So I've just made this connection here. I've connected that node A to the +5 on the power supply, node B to ground. So I've just made those. So now my circuit really is complete. Okay, so let me start up the waveform software here. Okay, so let's start up a power supply. Click on supply. Let's set the voltage to 5 volts. So this is the V plus terminal, right? This is the V minus terminal. I don't care about that. I'm going to shut that one off. It doesn't matter, but shut it off just to not confuse myself. So 5-volt power supply. You have to. So that's turned on, but you have to turn on the master enable. So now my circuit should have 5 volts applied to it. Let's check that. The first thing I like to do is check power supply voltages whenever I'm about to test a circuit. So in the spirit of having red and black terminals for a voltmeter, I'm going to take a red wire and plug it into the orange wire, right, if that's not confusing enough. I'm going to take the orange with white stripe. I'm going to plug in, I wish I had a black wire. I've got a brown wire. So now these two wires are my voltmeter. So the plus side of the voltmeter is the red, the minus side of the voltmeter is the brown. So let's check it. Let's just plug this into the power supply nodes there and there. So I should see, if I'm lucky, 5 volts when I start up my voltmeter. So let's go back to the welcome screen. Let's click on voltmeter, click on run, and that's good news. 4.993 volts, that's close enough to 5 volts for me. Okay, so I believe that now between these two nodes, I have 5 volts. I've measured it. I'm sure of it. Let me move this off the screen a bit. Okay, so I trust that between A and B, I have 5 volts. I'm measuring that. Okay, let me tell you this, that when I built this the first time, the voltages weren't what I expected. Probably, I don't know, 20% of the time I build a circuit, I get it wrong. I've got a wrong value resistor. I've got the wrong lead. You know, I maybe accidentally am one hole off. That is very common. So don't feel like you need to get this right. In fact, don't expect to get this right when you build a circuit all the time. I would say maybe 20% of the time getting it wrong is probably generous. But that's why we have measurements. If we could design something and build it and we were sure of it, we wouldn't need testing, right? You just design it, build it, and ship it. We test for a reason. And so the key here in lab is to learn how to troubleshoot. So the first step for me is to measure power supply voltages. And I've just confirmed, as you see on the screen, 5 volts there. Okay, let's measure this voltage. Let's go up and measure VAD, right? So VAD, that's VAD, right? Double subscript notation. I put the positive side of the voltmeter at A. I put the negative side at D, and I measure a voltage. And I get that voltage. Right? So I'm measuring 1.87 volts across resistor R2 with the polarity I'm showing here. Okay. Be sure to use both leads of the voltmeter, the 1 plus and the 1 minus, the orange and the orange with the white stripe. Because let me show you what happens. If I pull this orange with white stripe, the negative lead, out, and I just leave it floating, I just hang it in the air, look at that, you get 5 volts. The reason is inside the AD2, there's what's called a weak pull down resistor on the ground. So I wouldn't count on that working all the time. But essentially, when you only connect one voltmeter lead, just the positive lead, you're measuring the node voltage with respect to the AD2's ground. Now, what I would really do to be sure is I would plug, if I really want to measure that voltage where the red wire is with respect to ground, I'd plug the orange with white stripe into the ground of my circuit. But if you pull it out, you'll notice nothing changes. Right? So if you want to measure across a resistor, be sure to use both voltmeter leads. Okay, so now it just went to 8.74 volts, or 1.874 volts. Okay, if I want to measure, let's suppose I want to measure VEC, right? VEC, so VEC is plus minus VEC, like that. Okay, so let's pull these out. I put the positive side where I want to measure the positive side of the voltage. Negative side there, right? And I get, what did I get there? Minus 0.677 volts, 676 millivolts. If I want to measure VCE, right, plus minus VCE, right, double subscript notation. I just reverse the wires there. So that's VCE, and as expected, VEC is negative VCE, right? So when you switch the polarity, your reference polarity, when you switch it, you get the negative value of whatever you had before. Okay, if I want to calculate the current, let's suppose I want to calculate the current through resistor R1, down through R1. I'm going to measure the voltage. So let's suppose I want to do this. I want to calculate the current down through R1. Let's call it I1. All right. I'm going to use Ohm's law to do that. So I need what we're going to call that? We're going to call that VAC. So VAC. So Ohm's law says you have the current pointing into the positive sign of the voltage, and then V equals IR. So VAC equals I1 times R1. And so I1 equals VAC over 1,000. Right? And so what did I get a V? Let's see, I have it hooked up, double check that. I'm getting 2.478 volts. Let's call it 2.48. 2.48 volts divided by 1,000 equals 2.48 milliamps. Okay, so I've just calculated the current from a measurement through R1. So that's how you can measure current with the AD2. You actually measure voltage and calculate current. Okay. So the rest of the lab really is calculating the voltages across all the resistors. You're going to do a KVL around a loop, like one of these loops. You're going to calculate power. So for example, the power for, let's see, we're going to fit this. Power for resistor R1, P1, is equal to V squared over R, VAC squared over R1, right? So it's whatever it is, right? So 2.48 volts squared over 1,000. It's also equal to I1 times VAC, right? I times V. It's also equal to I squared R, I1 squared R1. So I would calculate it, if it were my lab, I would calculate that power 3 ways and make sure that all of those match. Because what that says is if all those values are the same, you probably have VAC measured properly, I1 measured properly, and you're using the right R1 value. Okay. And then you're going to add up the powers absorbed by all the resistors, the sum of those powers. That should equal the power delivered by the source to the circuit. So 5 times I in, it should equal the sum of all those powers absorbed by the resistors. Okay. So, you know, I guess that's lab 3. Did anyone run into any problems during the lab? It'd be great to share if you had any issues. It might help me and others avoid problems.
I think I initially just like didn't know how to start setting up the circuit because there was like a lot of different elements. But the way you just kind of worked through it helped a lot with like pointing out like I didn't really think of each bar as like a node, so that was pretty helpful for me.
Okay, great. That's good. I think that's really important that you know, when you finally get into lab, right? It's you see that dot right there is, I mean, it's part of a node, but it's not the whole node. If you think of the node being the entire, right, the entire connection between circuit elements, I think that really helps. You know, the schematic, all it really describes is what is connected to that node. A 5-volt source is connected to that node, R1 is connected to that node, and R2 is connected to that node. And you could shape that node any way you want, but once you make those connections to that metal node, then that part of the circuit is right.
Yeah, that's super helpful. And I think like also just like kind of knowing where to put each end of the voltmeter. But I just kind of had to like sort of trial and error it to get like what I got in the pre-lab, I guess, to like kind of figure out how that worked.
Does it make sense now?
Yeah, it does. Thank you.
Okay, sure. Yeah, just, you know, wherever you define a voltage, put the orange wire where you want to measure the positive side, and the orange with white stripe wire where you want to measure the negative side of that voltage you define.
And I think for measuring node voltages, you keep one end of the voltmeter grounded, correct?
That's exactly right. So I'd move this orange with the white stripe down to whatever I've defined as ground. And then everywhere else I touch in the circuit is a node voltage. And I think that's something you see in lab, and it's not so clear like in class when you're just looking at a schematic. But for example, if you look at the upper right node, V3. So let's measure node voltage V3. On the screen, you see V3 is 3.117 volts, right? Let's call it 3.1. If I move that wire to another place on that same node, if I move it, let's say 1 hole over, right? Just 1 hole over to the right, you see the same voltage. If I move it to the other side of this resistor, but connected to the same metal, right? You see the same voltage. If I take it out of the hole and I just touch it to the metal of that resistor, right? Just not even in a hole, it's just touched to that wire, you measure the same voltage. So anywhere you can touch the metal that's connected to that node, you're going to measure the same voltage. You know, I can take, you know, if you want to, sometimes I draw, let me get another wire here. Sometimes I draw a, like when I'm measuring between nodes, they say, well, let's draw a wire. Let me take a wire and put it from that V3 node, or with this green wire. Now let me move it down here. Some folks don't like that. So, well, how can you do that? You just added a wire. Doesn't that change the circuit? Well, no, I've extended that node. I've extended that node from the upper right down to, well, this kind of bottom empty set of holes here. But if I take my measurement down there, you're going to see the same voltage, right? So I just plugged in essentially to node V3, but at the bottom here. And again, you see 3.12 volts. So in class, if you ever want to do this, if you ever want to say, you know, you don't like that node there, you want to put it down here, you could take a wire. I'll draw this on the paper here. You can take that a wire, draw it in. Just okay. I've just put a terminal down at the bottom. That is now node V3. It's the same node. It's just I've extended it with a wire. That's what I did on the breadboard here. Okay, now that I made a mess over here. Other questions? Has anyone finished lab 3?
Yeah, I finished it.
Okay, did your calculated results match your measurement results pretty closely?
They did for the most part. I just I made some like an algebra mistake in the first step of the pre-lab. So I had to like recalculate all the pre-lab values. But once I did that, they like matched pretty closely.
Okay, like I said, that, you know, 20% of the time I get it wrong, and that's probably generous to myself. So
Yeah.
the measurements, you know, what's nice is it's one or the other. It's either we built it wrong, measure it, well, one of 3 things. We built it wrong, we measured it wrong, or we calculated it wrong, right? So we
Yeah.
mess up there, but that's absolutely normal. That's
Okay.
so.
Good to hear.
Okay. Well, I hope this helped. If you have any other questions, you know what I like to see on Slack is if you have an issue, take a picture of your breadboard and try to make it so that the resistors are visible and the wires are visible, so I can see which leads are connected to what. Also, send along a schematic because I want to make sure that what you're intending to build is what you built. I can help with that too, but definitely send along a schematic. Also make sure, I noticed this in someone's circuit, if you pack your resistors too closely, and it's hard to do here, but if I could bend these resistors, for example, such that these 2 leads touched together, that would actually combine those 2 nodes. It would be a short between those 2 nodes. So when you're building your circuit, make sure that you don't have any unintentional touching of leads from one resistor or one component to another. If it's the same node, it doesn't matter. Like for example, if this resistor and this resistor, if their leads were touching together on that corner, that doesn't matter. They're connected anyway at the same node. But if the bottom side of this resistor somehow was bent over and touched some other node, that would be bad. That would just cause your results to be wrong. So okay. Well, if there are no other questions, I'll end it here. Thanks for joining, and definitely keep active on Slack, and I'll be answering more questions there.
Thank you.
Thank you for doing this. It definitely made everything a lot more clear.
Great. Thanks for joining.